Good morning, everyone. It's a group B, right? Yes, okay. Hello everyone, good morning, how are you this morning? Fine, are you happy?
No.
No? Why? So you're going to have exam?
Yeah, exam.
Oh, come on. Exam is not... You should be happy to be here.
I hope physics 2 is easy an exam.
Is it easy?
I hope it's easy.
Ah.
It's easy.
Oh, it will be easy.
Just study harder so I can receive good marks.
No, don't. Okay. Just about this. Don't try to have a good mark. This is the ambition of bad students. Bad students try to have good mark. This is the ambition of bad students. Good students try to understand everything. And if they understand everything, they will have a good mark. You understand the difference?
Yes.
Okay? So, good students try to understand and to do the exercise, to try to solve the problem. Okay, this is only the good way to have a good mark.
So you mean that the bad student sometimes cheat and good student is study hard?
No, I'm not talking about cheating. I'm just telling that if your ambition is only to have a good mark, okay? If your ambition is this is the ambition to have a good mark, you will have something like this. But if your ambition is higher than this, then you will necessarily have a good mark. Okay, so let's start. Normally I should start a new, the second part, the magnetism part, but I have to finish the electricity part. So with the last chapter about electric circuit, so I will go in fast it is an easy chapter, so don't worry, you will do some exercise, okay? I would like to give the good definition. Okay, let's go. So, first part. So, what is a single loop circuit? Okay, so here is a single loop circuit, for example. Okay, so a loop circuit is an ensemble of electric device connected by by wires, okay, to form loops that form a loop, through which there is a current. Let's say flow. Okay? So, in this scheme, this is the wire, this is the device, okay? And in the device, in the loop, there is a current E going through it. Okay? So this is an electric device. Okay, so of course, can you read me? If there is a current flowing through the loop, so necessarily there is among the devices there is one particular device which maintains the current, okay? And this device is called the electromotrice device, electromotrice force. So, to maintain a steady current, one of the device must maintain a potential difference between its two ends. Okay, so among this, there should be a device which maintains, for example, this difference of potential. Okay? If there is no such a device, there will be no current. Okay? So this device is called electromotrice force, and it's EMF. Okay? Of course, you know already several examples of EMF. You have already the battery, okay? But you have also, for example, the solar cells. You know what is it, solar cells? Yes? You have electric generator, etc., etc. All these devices, batteries, solar cells, etc., etc., are called electromotive force, EMF. Okay? Okay, and of course, the EMF. Okay, so now we can distinguish two kinds of electromotive EMF. We can have ideal EMF. Okay. They have no resistance. So, of course, I didn't mention it, but the symbol of an EMF is like this, you already know. Okay? So, here, the EMF maintains between its two ends the difference of potentials V plus minus V minus, and by definition, so, by definition, we note Xi, it's a Greek letter, is equal to V plus minus V1, and in the circuit we symbolize Xi by an arrow going from minus to the positive sign, okay, like this, and with a small circle here to symbolize the EM. Okay? So this is an ideal EMF. But in the case of real EMF, real EMF have an internal resistance. So this is EMF. And in that case, for example, V plus V minus, or in that case, the C, in that case, it's not here. So V plus, V minus is here, V plus is here, okay? Because V plus and V minus are the two potentials at the end of the EMF. But in that case, the EMF is like this. And here, see, is lower than the difference of potential V plus minus V1. Okay? Okay, this is a single definition. So now let's start some problem. And with the general problem of how to calculate an electric current in a loop circuit. How to calculate a current in a loop. Let's wait. Okay, so let's consider this example. So now, for example, I can say that. Okay. So we can define always 2 points around each devices. Okay? Here, here, and here. Okay. So let's say A, B, C, D, E. Okay? So these points are points around each electric device. Okay? So to calculate the current in this loop, so we are looking for the current here, for example, which is also here. And the question is how to calculate it. So to calculate this, we are going to use a rule which is known as the Kirchhoff rule. So Kirchhoff I think that's the Hoff rule. And this is, you can say that according to Kirchhoff rule, the algebraic sum of all potential differences around all the loop a loop must be 0. Okay? So this is important. The algebraic sum of all the potential difference around a loop must be 0. Okay? So in that case, we have to say that, but in fact it's a kind of mathematical rule. Okay? In fact, we can say that V around the, for example, we have VB minus VA plus VC around the wire, for example, VC minus VB plus VG minus VC plus VE minus VD, etc. plus, VE minus VA. Okay, so I have started from here. This difference of potential plus this one, plus this one, plus this one, plus this one should be 0. Okay? But in fact, it's only a mathematical point of view because you can see that all the terms BB are disparate, VC, etc., etc. Okay? So this is a simple rule, and this rule will help us to calculate the current. Okay, so let's take an example, of course. Do you want me to put back this? Yes. Ah, great.
In the formula, we have VB minus VA plus VA minus VB. C minus VB plus That was should be VA minus VE.
Thank you very much. You are absolutely right. Thank you. Yeah. Okay, this is VA. It should be VA minus VD, of course. Yes?
Must be what?
0.
Thank you.
Any other questions? Okay, so let's consider an example, of course, to be sure. So, example. So the simple example that we can have is a resistance and a battery. If you connect a battery to a resistance, okay, so the resistance is R, let's say the EMF here is that direction, okay, and of course we have, as I said before, the points A, B, C, D. Okay, I will take, so, and the current is here. And here is the current. So again, what is the current here in the loop circuit? So if we apply B minus BA plus BE, C minus BB plus BD minus BC plus BA minus BD, so we have 0. Okay? So VB minus VA, this is C. Okay? VC minus VB, so you should know that the difference of potential around a wire is 0. Good. VD minus VC, okay, so here VD minus VC, I will tell you that it is, what is it? Minus, so minus R times the current, okay? And BA minus BD, it's the difference of potential around the wire, it's also 0, okay? So at the end, of course, E equal C over R. Okay, so few remarks. Of course, the potential difference around a wire is 0. Okay? There is no difference of potential around the wire. Okay? Okay, so when around a resistance, when moving in the direction of E, okay, so this is the case, delta V equal minus RE. Okay, so here, for example, if you are going to this direction, so it's the direction of E, so VD minus VC equals 0. Okay, so for we say that delta V like this. Okay, but of course, when when moving in the opposite direction, so delta V equal plus RE. So in that case, you have this. Okay? So you should just keep in mind that delta V, the difference of potential, is a kind of vector. Okay? It's not the real vector, but it's a kind of. Okay? It's always V plus delta V is the V of the arrow and minus the V of the. And if the arrow is in the same direction of I, then you have to put minus RE. And if the arrow are opposite to I, then delta V equal plus RE. Okay? And it's also the opposite remark around an EMF. Okay? When moving in the direction of E, so for example, so here, for example, okay, so delta V is here, E is here, okay, and C is here. C equal plus delta V, okay, or delta V equal plus. But when moving in the opposite direction, so for example, here, so imagine that E is here and C is here. So delta V is here. Okay. So here delta V, oh sorry, C equal minus delta V. Okay. So it's the opposite sign of the resistance. Any question? It's okay? It's easy, right?
Yeah, my question.
Sure. Go ahead, please.
Why does the moving
The moving means that the difference in potential, okay, it's like a vector, as I said, okay, so it's let's say let's do my remark. Zeta V equal V, let's say V I minus VG, okay, is like a vector from going from to J here to I. Okay, so if you have something like this, you have a device, you have I, J, okay? So if I, okay, let's see, I, you have an electric device surrounded by the 2 points I and J, the delta V is, if you write that delta V is Vj minus Vi, so it's a kind of vector, okay? It's here. Okay? So, and after that, you have two situations. Either the I is going in that way, either the I is going in the other way. Okay? So, okay? So, for each device, you have always two situations, two different. Okay. So if you define delta V is a vector, you can have that is moving in the direction of E is this. In that case,
Yes.
moving in the opposite direction is that case. Okay. It is moving in the direction of E, and in that case is moving in the opposite direction. Okay? Any other questions? No? Okay, so let me finish with some problem with several resistances. So okay. Yes? Question? You want me to put back this? You're welcome. Okay. Okay. Yes?
Yeah, I have to take a picture.
Okay, take a picture.
Thank you.
Okay, so let's study the problem of several, let's say 27 circuits with several resistances. Okay, so let's start with resistance in series. Okay, so let's consider this circuit. Okay, so you have one battery or one EMF characterized by the EMF C. You have one resistance R1, one resistance R2, and one resistance R3. Okay, and the problem today is to calculate the current I. Okay, in the circuit. Are you okay? Okay, so let's do it together. So, as usual, we always can define points, 2 points, okay, around each device, so we can have. So now I'm not going to consider the wire, okay, so of course, because you have A, B, C, D. Okay? And we are going to apply the Kirchhoff rule. So according to the Kirchhoff rule, so we can apply that V, so, okay, delta V A B, it's like a vector, okay, delta V B C plus delta V C D plus delta V D A equals 0. So this is equivalent to VP minus VA plus VC minus VB plus VT minus VC plus VA minus VD. Okay? It's the same. Okay? Okay? Yes? Okay, so now, what is it VP minus VD? So it's C. VB, VC minus VB. So, as I said before, you can draw some kind of, okay, it's not a vector, it's only a way to remember. So you can say that delta V BC is like this, because V, delta V BC, okay? Here you have delta V DC, okay? And here you have delta V A DA, okay? And then you have here delta V BA. So this is only a way to remember how to do this, okay? So here you can see that delta V BC is in the same direction of E. Yes, it's okay? Okay, so we have to write that this is minus RE, R1E. It's okay? Plus, similarly, you can see that delta DC is in the same direction of the I. So I have to write this is minus R2 I. And similarly, the third one is minus R3 I. And this is equal to 0. Okay? So at the end, obviously, you have I is equal to C over R1 plus R2 plus R3. Okay? And this is equal to C over one equivalent resistance Okay, so if you put several resistances in series, it is equivalent to one unique single resistance REQ with REQ equal R1 plus R2 plus R2. Is it okay? So if you put several resistance in series, it's like you add the resistances. Okay? Okay, so now let's see the other case. It is resistances in parallel. Okay, so now we have this kind of scheme. Okay, so C is here, R1 is here, R2 is here, and R3 is here. Okay. Okay, so here let's consider so here there are two junctions, right? There is one junction here, I mean at least. Okay, so here let's assume that the current EI is here. Okay, we are going. We can imagine the current going from this. Hello, yes, from this, from the battery going to this, and here at the junction A, the current will be divided into two sub. Okay, so maybe I prime here, and here maybe it's I1. Okay. Then the current I prime here is encountering a new junction at the point B, and so we can. Here we have the I3 and the I2 here. Can you see that? Okay. So at junction A, we can say that I equal I1 plus I prime. And at junction B, we can say that I prime is equal to I2 plus I3. So the current I is equal, of course, of I1 plus I2 plus I3. Okay? Okay, but now if I consider here A, B, C, so C is here, G is here, E is here, and F is here. Okay, can you see my 6 point? A, B, C, D, E, F. Okay? So, E1 is here. I can say that E1 is equal to VA minus VF over R1. Yes? Yes or no? Yes? Okay, good. Similarly, I2 is equal to VB minus VE over R2. And I3 is equal to VC minus VG R3. But, okay, you can see that VA, because A, B, C are just connected by wires, so they have the same potential, right? So VA equal VB equal VC, okay, equal V plus here. And similarly, the point D, E, F, and here have the same potential. So VG equal VE equal VF equal V minus, for example. Okay. So this is equal to V plus minus V plus minus V minus over R1. Similarly, here V plus minus V over R2 and V plus minus V minus over R3. Okay, so, and of course, V plus minus V minus is equal to C. Okay, so at the end, E equal C 1 over R1 plus 1 over R2 plus 1 over R3. Okay? And we can say that this is equivalent of one resistance with So this loop circuit is equivalent to one battery and one resistance, like this. But now the equivalent resistance is such that 1 over R is equal to 1 over R1 plus 1 over R2, etc., etc. Okay? Any question? It's okay? Okay, so let me finish with some very basic things. Remark. So, I don't, 37, 4. So, in the case of batteries in series, batteries in series or parallel, or sorry, or okay, so let's start by the case of battery is in series. It's easy. So if you have several batteries, like this, for example, so if you have C1 in that direction, C2 in that direction, but C3 in the opposite direction, okay, this is equivalent to only one battery with C equivalent with the electron of EMF equivalent is only the algebraic sum of the EMF. Okay? So of course this is only to remind you that if you want to increase the power of a battery, you can connect several batteries in series, but you have to connect them in the same direction, plus with minus, okay? Be careful of the sign. It's okay for you? Easy, no? Okay, more complicated. So in the case of batteries, in parallel, so this is more complicated. So now let's. I need to consider that we have batteries. Can I Yeah, maybe. Okay. So imagine that you want. Okay, I need to same batteries. So imagine that you have this. Can I imagine this? Yes, okay. Okay. So here, of course, I didn't mention in the case of batteries in series, I didn't mention the intrinsic resistance because it's easy. But now, imagine that we have 3 similar batteries, identical C batteries. So we have C here, and C here. And imagine that they have several different internal resistance. Okay. Okay. So this is, so imagine, okay, so we have A here, B here, and C here. And let's consider the point A prime, B prime here, and C prime. Okay, so the trick here, and that's why we need this assumption. The trick here is because we consider here identical batteries. So C equal C here. The point A prime, V prime, and C prime, you can see that they are not connected, right? But because we have identical batteries, necessarily the potential at the point B prime and A prime is equal to the potential at the point C primes. Okay, even if A prime, B prime, C prime are not connected by wire. Oh, there is no more. Okay, do you see this? This is an important thing to note. Okay, in this circuit, A prime, B prime, and C prime are not connected by wires. Okay, but because the batteries are equal, and this A, B, C are connected, so necessarily A prime, B prime, and C prime have the same potential. Okay? So this is a trick that I can give you. Try to identify in a circuit which points, have the same potential. Okay? So, of course, this indicates that, thus, VA minus VA prime equal C, VB minus VB prime equal C, VC minus VC prime equal C, and and thus we have this kind of equivalent now. Okay, so this because in fact the three batteries in parallel cannot produce more power like this. Okay? And of course, because we have three here resistance in parallel, we can calculate the equivalent resistance. Okay? So batteries, so it's not very useful to put batteries in parallel. Okay? This is the conclusion. Because at the end, you will have EMF, an equivalent EMF, which is equal to one EMF of one battery. Okay? Okay, so now I want to finish this chapter with a definition of what is an ammeter and voltmeter. I think that you already know this. Okay. So imagine that we have this circuit. Okay. So and this circuit. Okay, so what is by definition an ammeter is a device to measure the electric current in a loop, in a circuit. So imagine that we want to experimentally measure the current I. So we will need to insert the ammeter in series here. A. Okay. So an ammeter is a device to measure the current in a loop. Okay. It must be insert in a series manner. In the loop, into the okay. And one particularity of an ammeter, it should have a very low resistance. Okay? In order to not disturb the current in here. Okay? Okay? So an ammeter is a device to measure the current, and it should be inserted in a series manner. Yes? Okay. And finally, what is it? A voltmeter. It's a device to measure a potential difference between 2 points of a circuit. Okay. And to measure this, for example, if you want to measure the difference between this point and this point, okay, so you have to insert a voltmeter in a parallel manner, like this. Okay, so it must be connected to the 2 points in a parallel manner. And the last point is a voltmeter should have a very large resistance to this, in order to not disturb the current. You have any questions? No? Okay. So, I have finished the first part of my lecture about electricity. So, please, if you have any question, it's the time, it's the moment to ask me any question about electricity. Okay. So now I am going to start the second part of my lecture is about magnetism. Okay? Okay, so magnetic phenomenon was also discovered a long time ago, thousands of years ago, in fact everywhere on Earth, because the human beings have discovered that in the nature some stones, some materials have the property to attract some metals. Okay, so this is a very common in Earth. Okay, some materials have the natural, without doing anything, the natural property to attract metals over a short distance. Okay? And the men or the human beings who discovered these stones, these materials, they think that it is magic. Okay, so they call this stone magic stone, but at the end it ends with magnetized stone. Okay. This magnetized material are called, and after that we call them magnets. Okay? So if you are lucky, you can find in the nature some stones which are natural magnet. Okay? Okay, and as you may know, I will present you this. Magnet creates around them a magnetic field. Okay, so we are going to describe this. So chapter 28, magnetic field. Okay, so to present you the magnetic field, I will do a kind of similarity with the electric field. Okay, so I would like to remind you that a charged material create or produce an electric field. You remember this? Do you remember an electric field? E. This electric field generates a force on the charge, okay, which so, and the force now, you know that this force is equal to QE on a charge Q. Okay? So, by definition, E equal F over Q. Okay? So this is a reminder. But this reminder will help us to understand what is a magnetic field. So similarly, a magnet or a magnetic stone, okay, magnetized material or magnet, okay, produce, this is an S, sorry, produce a magnetic field. So we are going to call it B, okay. So this magnetic field cannot be filled like this, okay. But if you put in the magnetic field a charge Q, but a moving charge, then you will see the force, okay. So this magnetic field produce or generate a force on a moving charge. This is a new thing now. A moving charge Q, and the force, which will be called FB, is Q times V dot product times B. Okay. So this is the first way to define what is it a magnetic field B. And in this formula, this is important to note that this is a cross product, not a dot product. Okay? Let me. Okay. So do you know this operator, this mathematical operator, the cross product? So the cross product is an operation between two vectors, and it gives a third vector. Okay? Okay, so I don't know if you mind. So of course, by definition, sorry. forgot, but it is implicitly a magnetic field B is the vector which generates the force FB on the moving charge Q with the velocity of velocity v. Okay, and again, Fb is equal Qv times v. Okay, so just some remark about the cross product. So imagine that we have a plan here, okay, and imagine that we have a particle here, okay, and imagine that, for example, the particle is going in that way with the velocity v like this, okay? And imagine that we have a force field, sorry, no, sorry, not in that way, but okay, let's see, like for example, B. Okay, so it's not obvious here, but okay. So this is the plane perpendicular to V. Include here. So by the property of the cross product, say that the force B so will be in that direction. Okay. So by definition, maybe FB is always perpendicular to B, and FB is always perpendicular to B also. Okay? And the direction of FB is indicated by the very important right hand rule. Okay, so what is this right hand rule? Okay, so I'm going to try to make a clear diagram. Okay. So again, so now imagine that B is going like this, and now B is the same plane. Okay, B, Q. Okay, so imagine B is like this. But in the same plane, okay? hand, I'm going to try to draw this. It's not easy, but yes, exactly. So imagine it's a free. So, yes, it's not okay. So, you take the right hand, you put the fingers around the bit of V, okay, and the palm is perpendicular to B, okay. Here. Then the thumb will give you the direction of FB. Okay, so of course I am assume that's a positive, so FB. Okay, so can you see me here? Okay, so what is the right hand rule? So this is, for example, the vector V, okay? And imagine that the B vector is like this, okay? So I take my right hand, I put my fingers in the direction of V, okay? So I can move my hand, and I oriented the palm of my hand toward B, okay? And then my thumb indicates the direction of FB. Okay, so I'm going to write this like all fingers except thumb are oriented to B. The palm, okay, you understand the palm of the hand is oriented toward B, and then the thumb indicates the direction of FB. Okay? Yes, please ask me any question. Yes? Okay. Okay. So imagine that this is the vector B. You have to look at me. Okay? Imagine, I don't know, this is for example the vector B. Yes? Okay. No B. No. B is oriented by the palm of the hand. Okay? The palm here. So, for example, B is here. B is up. So my palm is oriented toward B. Okay? And then my thumb is going to indicate. So in that case, the vector FB is toward B. Yes? It's okay for everyone? Do you know this? This is a property of the cross product between two vectors. Is it the first time that you see that?
No.
Okay, so the vectors B, the palm, and the B.
So that means that
No, the thumb is indicating the force, the third one. Okay?
Okay, I understand.
Can you can we go on? Okay, so again, the magnetic field B is defined by the effect that it has on a moving charge. Okay, it's important to note this. By definition, the magnetic field is a vector which generates the force Fb equals to E times B. It's okay? Yeah?
I understand.
Okay, so now okay, let's make a remark about the magnitude of B. Okay, so first case, if V and B are parallel. In that case, there is no force because due to the property of the cross product, a cross product between two parallel vectors is equal to 0. Okay? So FB equals 0. Okay? If V and B are not parallel, then we can say that the magnitude of the force V is equal to the absolute value of the charge times V times B, okay, times sine theta, where where theta is the angle between V and B. Okay, so for example, here V theta is here. Okay? So of course, from this, you can say that B, the magnitude of B, is equal to the magnitude of the force divided by Q V sin theta. Okay? Yes?
This must be cos.
No, it is not cos, it's sinus. Because the cos is only for the dot product. Here we have a cross product. Okay? So it's a sinus. And you can see that if theta is equal to 0 or theta is equal to pi, so that means that the two vectors are either opposite or the same direction, so it's parallel. So you can see that the force is equal to 0. Yes?
Yes.
Okay, so of course, the unit of B, of the magnitude field, you can see that it's Newton over Coulomb meter second minus 1, which is also Newton over ampere meter, and this by definition is Tesla. So the unit of a magnetic field is Tesla, and it is noted T. It's okay? Okay, so of course we cannot see magnetic field around us, but we can imagine them, and similarly to electric magnetic to electric field line, we can define magnetic field lines. Okay, so similarly to electric field line, we can imagine or draw magnetic field lines. So I remember which are tangent to be and oriented to the direction of B. Okay, so let me show you some examples. Okay, so if you have a magnet, let's say like this, okay, we can observe, and this is, we can observe that the magnetic field lines are all exit from one end of the magnet and all enter into the other end of the magnet. And so we have something like this. So, a bar magnet. This is a bar magnet. B-A-R. Like a bar. Okay? So, we observe we can observe that the magnetic field line exits from one end of the magnet and enter into the other end. Okay, and these two ends are called, we say that a magnet has two poles. Okay? A north one and a south one. Okay? And by convention, the north pole is the pole from where the magnetic lines are existing. So this is B, of course, B, D. Okay? So the north pole is the end of the magnet from where the magnetic field lines are exiting, and the south pole is the end to which the magnetic lines enter the magnet. Okay. We have also other kind of magnet, of course, and maybe you know this. This is a U magnet. This is a bar magnet, this is a U magnet. Of course, you can see that a U magnet has the shape of U. And if you define the north pole here and the south pole here, okay, you will see that the magnetic field is like this. Okay? Oh, yes, one remark. Because you may know that our Earth, is like a bar magnet. Okay, you know that around the Earth, and hopefully, there is a magnetic field. Hopefully, because this magnetic field protects us from the solar radiation. Okay, from the rays from the sun. The magnetic field deviates most of the solar radiation, and that's why we can live on Earth, okay? And this is maybe a problem, because if we want to go to Earth, to Mars, you know, planet Mars, so we will need to exit the magnetic field of the Earth, and we will not be protected anymore. But the point is, very importantly, the point is that if you consider the Earth like this, okay? So the Earth has a north, of course, but this north here and this south are called geographic north or geographic south. Yes? Okay, so this is the geographic pole. But we know that in fact the Earth is a magnet, but the pole, so this is a magnet of the Earth, let's say. But the magnet of the Earth has the north, the magnetic north, in the south, in fact. So this is the magnetic pole. And this is the magnetic north, pole north. Okay? So, it's just like this, okay? Don't worry. So the magnetic field of the Earth is going from the south, in fact, to the north. Okay. This is not important. It's okay? Can I continue? No, 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 no. No, no. At what time do you have to finish? At 12. At 12:10. Okay, thank you. Okay, so this is B. This is group B.
Yes, B.
Okay, so now let's study. So as I said, as I said, the magnetic field is defined by its effect on a moving charge. Okay, so now let's study in more details the behavior of a moving charge in a magnetic field. Okay, so let's read, I guess. And let's do some mechanics. Okay, so what is it here? This is sorry. This was 228.1 definition. Okay. Definition. Okay. So now 28.2. Force. Okay. Let's say motion. Sorry, motion of a particle in a magnetic field. Okay, so let me first describe you the Thomson experiment. Thomson, I think that is a P, Thomson experiment. Okay, so this experiment, this apparatus was created by Thomson and was used to discover the existence of electrons. So what he did is he has a tube, a tube like this, okay, and there is a screen at the end. So okay, this is a tube, screen. Okay. From this, he this is a wire, okay? It's a filament, okay? And this filament was hit by a battery, okay? So, and just after the filament, so this is a hit filament, heated filament. Okay. And just after this, there is two plates of metal like this, but with the hole. Okay. So this is plates of metal with hole, with a hole inside. Okay. So and this plate was connected also to a battery. Like this. Okay, so what happened? So when the filament is heated, the filament emits some particles, okay, and the plate of metals, because it has charge, will accelerate the particle, so the particle will have a motion like this. Sorry. Okay? So the particles Q here, we have a velocity V like this. And then you will have a spot here. Okay? Do you understand what I mean? Okay, I repeat. The heat filament will emit it. So Q, spot of Q is an emitted particle, charged particle. Okay, so, and this is the, let's say, the plate. Accelerate the. Okay, so now let's consider that there are, after this, okay, there are two horizontal plates like this. Is it time to go? Oh, okay, sorry. Okay, I will finish. And imagine that the two plates also are connected to a difference of potential. Okay? So, then there will be, of course, an electric magnetic field within here, like this. E. But okay, so now so for you homework, what is, so you can imagine that, okay, we know that the particles are negative, okay, so we can intuitively, we know that the particle will be deviate here from here, right? Okay, and so my question is, just after here, just after the exit of the, what is the deviation y0? Okay? So this is There is for the time being, there is only an electric field, okay? And just after that, we will put a magnetic field, okay? Okay, so that's it. See you on Tuesday. No, see you Wednesday. No, not tomorrow. Thursday. Okay. Thank you for your attention.